Say the words data center to most people, and they picture a warehouse full of computers. That picture isn't wrong exactly, it's just radically incomplete. A data center is not a room full of servers. It's one coordinated machine, where electricity has to arrive continuously and without interruption. Heat has to be removed as fast as it's created. Thousands of individual computers have to be wired together so they behave like a single service. And every piece of that system has a backup ready to take over the instant something fails. Take away any one of those layers, and the servers themselves, the part everyone pictures, stop mattering at all. By the end of this, you should be able to mentally walk through a real facility. How power gets in, how it never stops, how heat gets out, how a request from your phone turns into an answer, and why none of it is allowed to depend on just one of anything. Start at the very beginning of the chain, before a single server has done any work at all. Electricity arriving from the outside world. A data center doesn't plug into a regular wall outlet scaled up. It connects directly to the high-voltage transmission grid, often through its own dedicated substation built specifically to serve that one facility. That incoming power arrives at a voltage far too high for any piece of computing equipment to use directly. So the first job on site is stepping it down through large transformers, then routing it through switchgear, banks of heavy-duty electrical switches and protective breakers that can isolate any section of the system instantly if something goes wrong, the same basic idea as a circuit breaker in a house. Scaled up to handle enough power for a small city. This entire front end of the facility, before any computer is even involved, exists for one purpose: taking bulk grid electricity and turning it into something the rest of the building can safely and reliably use. It's worth pausing on a distinction that gets blurred in a lot of casual discussion of data centers: the difference between IT power and facility power. IT power is what actually reaches the servers, storage, and networking equipment doing useful computation. Facility power is the larger total, including everything else described so far: cooling, lighting, the UPS system's own losses, and all the supporting infrastructure that exists purely to keep the IT equipment running reliably. The industry uses a metric called Power Usage Effectiveness, or PUE, to describe the ratio between the two. A facility with a PUE close to 1.0 is delivering almost all of its incoming power directly to computing equipment, with very little loss to overhead, like cooling and conversion losses. It's a genuinely useful engineering metric for comparing a facility against its own past performance, but it's easy to misuse. A low PUE number alone doesn't tell you how much total electricity a facility actually consumes. Doesn't account for how that electricity was generated, and can vary substantially between facilities simply because of local climate. A data center in a cold, dry region can cool itself far more cheaply using outside air than one in a hot, humid region. Independent of how well either facility is actually engineered, a PUE number is one useful data point among several, not a complete verdict on how sustainable or well-run a given facility is. Reliably is the key word, because grid power, however good it usually is not perfectly continuous. Voltage dips for a fraction of a second. Storms take down transmission lines. Regional outages happen. And a modern data center cannot tolerate even a brief gap, because the computing happening inside doesn't pause gracefully. An interruption of even a fraction of a second can crash running processes, corrupt data mid-write, and knock services offline that people and businesses depend on continuously. So sitting between the incoming grid connection and the actual computing equipment is a layer whose entire job is making sure power never actually stops, even for an instant, no matter what happens outside. The first part of that layer is the uninterruptible power supply, usually shortened to UPS, banks of batteries, sometimes joined by fast-spinning mechanical flywheels in some designs, sized to bridge the gap the moment grid power falters. The UPS doesn't need to run the facility for hours. It needs to run it for seconds to a few minutes, just long enough for the second layer to wake up. Backup generators, typically running on diesel or natural gas, sized to carry the entire facility's power load independently of the grid entirely. Generators take time to start and reach a stable output, usually somewhere in the range of 10 to 20 seconds, which is exactly the gap the battery layer exists to cover. The sequence is simple once you see it laid out. Grid power fails, batteries take over instantly and silently. Generators start and spin up in parallel, and once the generators reach stable output, the load shifts over to them, potentially for as long as the outage lasts. None of this is a single point of protection. Either most serious facilities run multiple independent UPS units and multiple generators, each sized so that even if one fails during an actual event, the remaining units can still carry the full load. Once power is flowing reliably, it still has to get from that central electrical room out to every single server in the building, and this is handled through a distribution network of busways. Heavy-duty enclosed conductors that run overhead through the facility like electrical highways feeding down into power distribution units, sometimes called PDUs, positioned throughout the rows of equipment. Each PDU steps power down further and splits it out to the individual racks. And at the rack level, it typically splits again into two entirely separate power feeds running to the same equipment, so that a failure anywhere upstream in one of those two paths, a trip breaker, a failed PDU, a fault in one busway, still leaves every server running normally on its other completely independent feed. This is the same underlying idea as the UPS and generator layer, just repeated at a much smaller physical scale, all the way down to the individual machine. Now finally, the part everyone actually pictures: racks of servers standing in long rows, each one a tall metal frame holding stacked computing equipment, connected by cabling running along the top or bottom of the row. A server itself is a purpose-built computer, stripped of anything a general-purpose desktop would need and optimized, instead, for density and serviceability, processors doing the actual computation, memory holding data those processors are actively working with, and network connections tying the whole machine into everything else in the building. Alongside compute racks sit storage systems, dedicated equipment built specifically to hold and retrieve enormous amounts of data reliably. Spreading information across many physical drives simultaneously so that no single drive failure ever actually loses anything. On average, across a typical modern data center, servers themselves account for around 60% of the electricity actually consumed by the computing equipment, with storage and networking equipment together making up a much smaller share, though that balance shifts noticeably in facilities built specifically around the newest, most power-hungry AI computing hardware, a distinction worth coming back to shortly. None of those racks matter individually, though. What makes a data center function as a single coherent service rather than thousands of disconnected machines is the network tying them all together. Inside the building, switches, dedicated networking equipment, distinct from servers, connect every rack to every other rack through an enormous mesh of high-speed cabling, often fiber optic engineered, so that any two machines in the building can exchange data with extremely low delay and enormous bandwidth. That internal network is what lets thousands, sometimes tens of thousands, of individual servers coordinate as one service rather than functioning as isolated islands. Sitting at the edge of that internal network are load balancers, whose entire job is spreading incoming requests evenly across the available servers so that no single machine gets overwhelmed while others sit idle, and routers connecting the whole facility back out to the wider internet through redundant fiber links, again, built with more than one physical path, so that a single cut cable somewhere outside the building doesn't take the entire facility offline. Every bit of that electricity, once it's done its job of powering computation, ends up as one final byproduct: heat. This is where the second major engineering challenge of a data center begins. Because dense racks of continuously operating computing equipment generate an enormous, unrelenting amount of heat, and if that heat isn't removed constantly, equipment temperatures climb until components throttle their own performance to protect themselves, or fail outright. In a conventional facility, cooling is handled primarily through air. Cold air is pushed up through the floor, or in through vents, at one end of a row of racks, pulled through the equipment where it absorbs heat, and expelled out the other side into a return path that carries it back to cooling equipment to be chilled again. Most modern facilities organize this using what's called hot aisle and cold aisle containment, physically separating the rows so that cold air feeding the front of the equipment never mixes with hot air exiting the back, which dramatically improves cooling efficiency compared to simply flooding an entire room with cold air and hoping for the best. Air cooling has real limits, though, and those limits are exactly where the newest generation of AI-focused computing hardware has started to break the conventional playbook. The specialized processors used for training and running large AI models draw dramatically more power and therefore generate dramatically more heat, packed into the same physical rack space as conventional servers, high enough that moving enough air fast enough to keep the equipment cool becomes impractical, or in some designs physically impossible within reasonable space and noise constraints. That's driving a shift toward liquid cooling, where a coolant is brought much closer to the heat source than air ever could get, either through cold plates mounted directly onto the hottest processors, carrying heat away through circulating liquid instead of air, or in some designs by immersing entire pieces of equipment directly in a thermally conductive fluid. Liquid moves heat away far more efficiently than air does for a given volume. Which is exactly why the highest density AI computing clusters increasingly rely on it rather than trying to push conventional air cooling past its practical limits. It's worth being clear that this is a shift happening in the newest highest density facilities specifically. Plenty of data centers running conventional workloads still operate perfectly well on air cooling, and the two approaches will likely coexist for a long time, depending on what kind of computing a given facility is actually built to run. Water use is another area worth resisting a single universal claim about. Some cooling architectures use evaporative cooling towers that consume meaningful amounts of water, while others, including many liquid cooling designs used for dense AI hardware, run largely closed-loop and use comparatively little water once operating, with the actual figure depending heavily on the specific cooling architecture chosen and the climate the facility sits in, rather than being a fixed property of data centers in general. All of this, power, cooling, compute, and networking, is watched continuously from a control room most visitors never see, filled with monitors displaying real-time readings from thousands of sensors placed throughout the building. Temperature and humidity at every row, power draw at every rack, the status of every generator, UPS unit and cooling system, and network traffic flowing in and out of the facility. Software platforms built specifically for this job aggregate all of that data and flag anomalies automatically. But human operators remain on site around the clock specifically because physical infrastructure at this scale can fail in ways that are obvious to an experienced engineer walking the floor long before a sensor threshold trips an alarm. That brings the whole system back to the concept sitting underneath almost everything described so far: redundancy. The basic idea is simple. Even if the engineering behind it isn't, for every critical system, have more capacity than you strictly need, and split it across independent paths, so the failure of any single component never actually interrupts service. A facility with what's sometimes described as N+1 redundancy has one more unit of critical equipment, whether that's a cooling system, a generator, or a UPS, than the minimum needed to run the full load, so a single failure can be absorbed without any impact at all. More demanding facilities go further, running fully duplicated, independently powered systems side by side, sometimes described as 2N, so that even planned maintenance on one entire path never affects service running on the other. That distinction matters in practice more than it might sound. A technician replacing a failed cooling unit, or a utility crew doing scheduled maintenance on one incoming power feed, is a routine, planned event in a well-designed facility, not an emergency, precisely because the redundant path absorbs the load the entire time without anyone outside the building noticing anything happened at all. It's worth being clear that not every data center is built to the same level of redundancy. The actual level varies significantly, depending on what the facility is designed to support and how much downtime its operator is willing to tolerate. And organizations like the Uptime Institute maintain formal tiers, specifically to describe and compare these different levels of resilience. The common thread across all of them, though, is the same underlying principle repeated at every layer of the building. Never let a single failure become an outage. Put the entire chain together, and you can finally follow what actually happens, physically, when you open an app or ask an AI system a question. A request leaves your device and travels across the internet to a data center, arriving through one of those redundant external network links. A load balancer decides which of thousands of available servers should handle it. That server, drawing power that arrived through the grid connection, was conditioned by transformers and switchgear, and is protected the entire time by batteries and generators standing by, pulls whatever data it needs from storage systems elsewhere in the same facility, performs the actual computation, and sends a response back out through the same network path. All while the heat generated by that entire process is being continuously carried away by the cooling system running in the background, and every piece of it is being watched in real time from the control room. All of that for a single request typically happens in a fraction of a second, invisible to the person who sent it, repeated simultaneously for millions of other requests, happening at the exact same moment across the same facility. It's worth being precise about scale and framing here, because the pace of growth in this industry recently has been genuinely unusual, and it's part of why so much attention is currently focused on power and cooling designs specifically. According to the International Energy Agency's 2026 reporting, global electricity demand from data centers grew by roughly 17% in 2025 alone, with demand from AI-focused facilities specifically growing even faster. And the agency's base case projection has global data center electricity consumption roughly doubling from around 2025 levels by 2030. That's a forecast, tied to a specific base year and a specific projection scenario, not an observed fact about the future. And it's worth remembering that data centers still represent a small share of global electricity demand overall, with the sharpest growth concentrated specifically in the newest AI-optimized facilities rather than the industry as a whole. What that growth curve actually explains at the engineering level this video has walked through is why power density, liquid cooling, and grid connection capacity have become such urgent design questions right now, not because data centers are new, but because the newest generation of computing hardware inside them draws so much more power and generates so much more heat than the equipment these facilities were originally designed around. None of this makes every data center identical, and it's worth resisting the instinct to picture one universal blueprint. A facility built for a specific AI computing cluster looks and behaves differently at the power and cooling level specifically. From a conventional cloud data center running a mix of ordinary business software, different rack density, different cooling architecture, sometimes different redundancy requirements depending on what workloads the facility actually needs to guarantee uptime for. What stays constant across essentially all of them is the underlying structure this entire walkthrough has followed. Power has to arrive and never stop. Heat has to leave as fast as it's generated. Thousands of individual machines have to function as one coordinated system. And every critical piece of that chain needs a backup ready to take over before anyone outside the building ever notices anything went wrong. The servers are the part everyone sees in photographs. Everything holding them up, invisibly, is the actual engineering story.